Hello, astronomy and astrophysics enthusiasts. If you want to take your passion for astronomy and astrophysics to the professional research level, IUCAA is one of the best places in India to do so. But getting into IUCAA isn't easy. You first have to clear a challenging examination followed by 2 rounds of rigorous interviews. In this video, I'll be sharing my complete second round interview experience, the questions asked, how the interview progressed, and what I learned from the process. Hopefully, this gives you a realistic idea of what to expect and how to prepare effectively for your own interviews. So without any further ado, let's get started. I was feeling nervous when I entered the room. There were 5 panel members in my interview committee, and I recognized one of the faces. He was at IIT Delhi when I took the INAT exam there. Looking at him, I felt easy. They also made sure that I feel easy and can focus on my interview and don't get lost in my own thoughts. So they didn't start with questions directly. They asked me where I'm from, have I already graduated, which university am I attending. So after all these small talks, they started with the real questions. One professor asked me, have you studied interferometer? Yeah, I know about interferometer. Michelson interferometer is the one I have studied. Then he asked me, can you draw the schematic diagram and how it works? I did that. I made the 2 meters setup where a beam of light is split into 2 parts and then recombined at the detector. So I drew this and told him that these mirrors reflect the light, and this is the source, and this is the detector. I explained all this. He seemed satisfied. He said, okay, yes, sure. Then he asked me about what's resolution in lenses, in microscopes, telescopes, and interferometer. And then he gave me an equation, and with that equation, he asked me, why is detection of gravitational wave tough? What can cause anomalies and error in gravitational wave detection? The one thing I knew already was thermal fluctuations, because gravitational waves have very small energy and amplitude when they get detected at Earth. Small fluctuations, thermal fluctuations, can cause errors. So I explained them that, and they were smiling at that answer, and I really felt comfortable from there. After this question, my confidence and my comfort, my easiness really skyrocketed. My nervousness slowed down. After this question, one of the professor asked me, have you studied classical mechanics? Then he asked, have you studied central force motion? And do you know about effective potential? Sure, I have studied all this and I know. Then he said, can you draw the effective potential graph for gravitational forces? I drew the effective potential for gravitational force of this thing. Then he asked, can you draw effective potential for inverse cubic force? Gravitational force is inverse square force. So can you draw the same effective potential, similar effective potential for inverse cubic forces? I found out V of R, which will be minus K by R square from here. And from here, I calculated V effective, which came out to be L square over 2M minus K times 1 by R square. You can do it yourself and check if it's correct. Then he asked me, can you draw a graph for this? There were 3 conditions. This L square over 2M minus K can be positive, negative, or 0. So there were 3 distinct graphs for these 3 distinct cases. I draw these graphs. Then he asked me, can there be circular orbit in this potential? Sure, there can be circular orbit. Will it be stable? I said, no, it won't be stable. I answered from the graph. The graph was of 3 distinct parts. There was this positive half, negative half, and then there can be one equals to 0, exactly 0. This horizontal graph can be there. There will be circular orbit when L square over 2M minus K will be 0. In this case, there will be circular orbit, but the orbit won't be stable because any perturbation can spiral the particle into the center or move it away from the center. And for positive L square over 2M minus K, when this quantity is positive, there can be parabolic and hyperbolic orbits, and when this quantity is negative, there can be spiral orbits, the orbit that will spiral inward toward the center. He seemed totally happy with the answer and then asked other professors if they have any question to ask. Then there was the next question where I was asked about momentum and energy of a photon. Its formula: energy equals h nu and momentum equals h over lambda, these formulas. And then he asked, have you studied special relativity? Have you done Doppler effect for photons? Then he asked, if there is a particle and there is a photon coming towards it, and if the particle is stationary, what will it observe? Then I said, yeah, it will observe the same thing that any stationary observer will observe. But if the particle is moving, there will be some red shift or blue shift depending on the relative motion. If the particle is moving towards the photon, there will be blue shift. If it is moving away from the photon, it will observe some red shift. Then he asked, what will happen if the energy of the photon is exactly equal to the transition energy of the particle? If it is an atom, the transition energy gap between two energy levels, if it is exactly equal to the energy of the photon, what will happen? I answered the atom will absorb the energy photon and re-emit it in any random direction. Then the professor that I recognized stood up and he asked me, have you learned Maxwell's equations and can you write them on the board? I remembered all the equations. So I promptly wrote all the equations on the board and got his approval that they are correct. Then there was an old professor. He asked me. He stood up and he said, "You already told you have studied classical mechanics. So have you learned about Lagrangian and Hamiltonian?" I said, "Yes, I have studied." So if I give you a Lagrangian, can you convert it into Hamiltonian? I remember the Lagrange transformation equation, which is Hamiltonian is equal to Lagrange P times Q dot minus Lagrangian. I remembered this equation. So he said, okay, let's have this Hamiltonian Lagrangian, where Lagrangian equals to mx x dot. Can you convert this into Hamiltonian? From the Lagrangian, I calculated P and then substituted this in the formula, this Lagrange transformation. And I was just about to reach the final answer and he said, okay, I'm satisfied. I know you can do it. This is just a high school algebra. Anyone can do this. Okay, I'm happy. You can stop here, and if you have any question, you can ask us now. If you have any questions or want me to make video on any specific topic, let me know in the comments below. Thanks for watching and see you on the way of physics.